Greetings everybody. My name is Paxaj Shukla.
And I am Aasheesh Tandon.
Today we are going to talk about tactile sensors. To give a brief overview of topics that we are going to cover today, first of all we are going to give a definition of tactile sensors and the different parameters that these sensors measure. Secondly, we are going to discuss different transduction techniques that such sensors employ.
Further, we will be discussing about 4 commercial tactile sensors which are very popular in the industry today, along with briefly discussing their specifications and the concepts on which they are based. Finally, we will be comparing these sensors. So come on, let's begin.
So, tactile means perceptible by touch, thereby a sensor which acquires some kind of information through physical touch is known as a tactile sensor. Now, how do we achieve this artificial tactile sensing? So, this can be done by measuring parameters such as pressure distribution, thermal conductivity, shape, texture, vibrations, by a direct contact between the object and the subject. As with the other sensors, performance criteria for tactile sensors also play a very crucial role in deciding its application. We have listed 18 important criteria in our paper for the sensors, which include sensitivity, dynamic range, elastic properties, response time, and etc. Moving on, let me discuss the different methods of transduction. Starting with resistive tactile sensors, this sensor typically consists of 2 conductive sheets separated by some insulation. When force is applied, the second sheet is brought in contact with the first one, and that point acts analogous to a slider in a potentiometer. This is used for locating the point of contact, and hence this forms the working principle of tactile sensors. Next, in the capacitive transduction technique, the area between the plates of the capacitor is varied, or the distance between them is altered by application of a force. The main advantage of such sensors are that they can be fabricated in very small sizes, which allows the construction of dense sensor arrays. For inductive tactile sensors, the working principle is similar to LVDT. When touch is sensed, modulation of phase and amplitude of induced voltage occurs, which displaces the movable core, thereby causing flux linkage from the primary coil to the secondary coil. In piezoresistive method, a piezoresistive crystal is used which changes its resistance on action of force. This change in resistance is observed by changing the voltage and keeping the current constant. Each taxil, that is the individual sensing element, contains this pressure sensitive crystal for effectively measuring the area of contact. The piezoelectric sensors work on a principle that a voltage is generated when a material such as certain crystals and ceramics is distorted. The voltage generated is directly related to the applied force. These sensors exhibit a very high frequency response, making them ideal choice for measuring vibrations. The magnetic sensing technique works by detecting changes in magnetic flux due to application of force on a small magnet. The measurement of this flux can be achieved by different methods such as Hall effect, use of magnetoelastic sensors, or inductors. In spite of several advantages, these sensors cannot be used in magnetic environments as they are susceptible to magnetic interference and noise. In optoelectric method, a light source, a transduction medium, and a photodetector is used. A CMOS camera is also employed to record the reflection pattern. The light intensity obtained in the diffused reflection indicates how close the object is to the surface. Again, these sensors are immune to electromagnetic interference. Next, the ultrasonic tactile sensors use polyvinylidene fluoride polymer rubber as receiver arrays to pinpoint the contact location. This technique enables slip and roughness detection even during motion. The next, which employs tunnel effect, in this, when quantum tunneling composite, that is QTC, is under pressure due to force, a rapid drop in resistance occurs, which happens without any contact between the particles. This is identified as quantum tunneling effect. This change in resistance produces a corresponding voltage output, which is used to detect the point of contact.
Okay, so now we will discuss about the commercial tactile sensors existing in the industry. The four most popular tactile sensors are capacitive type, variable resistive type, conductive rubber type, and quantum tunneling composite type. We have capacitive type commercial tactile sensors, the leading manufacturers for which are Pressure Profile Systems Inc. Their most popular product is Digitex system. The Digitex system by PPS has pads with a number of sensitive capacitive sensors embedded with digital output to enable tactile sensing in a variety of applications such as prosthetics, robot hand, etc. Many such sensors can be combined together to give a larger area of sensing, and thus it is scalable. It is equipped with microcontrollers and is easy to install. User interface is provided by PPS's Chameleon Tactile Visualization and Acquisition, providing common and often used features like exporting, saving, processing data, etc. Are certain characteristics of the sensor. Next up, we have got conductive rubber type tactile sensors, the leading manufacturers for which are Wise Robotics. Two of their most popular products are DSA 9330 and DSA 9205. These products are predominantly used for gripping applications and can be used on both planar and curved surfaces. They have high noise immunity and have a robust design. Even these sensors have electrical connections at their ends, and hence it is possible to feed the data directly into a computer. A standard point is the design to allow easy cleaning of the transducers, crucial to pharmaceutical and food processing industries. Here are certain characteristics of the DSA 9330 and DSA 9205. Next up, we have variable resistance type tactile sensors, whose leading manufacturers are Spectra Symbol. Their most popular products are soft pot membrane potentiometer, hot pot membrane potentiometer, and thin pot membrane potentiometer. These three sensors work on the same principle as that of a potentiometer. The soft pot membrane potentiometer is the thinnest sensor in the market today and is very simple to use. To be used, it just needs to be mounted on the surface. It is economical, has a high working range, and gives a linear output regardless of the shape of the surface on which it is mounted. Hot pot is used for applications requiring function at high temperature where precise position sensing is required. Thin pot is similar to soft pot but is even narrower. All of them have got a good linear range and a good temperature range, but the heat losses in all of them are quite much. Is a comparison between the three sensors and certain of their specifications. Last commercial sensor that we are going to cover today is the quantum tunneling composite type tactile sensors, whose leading manufacturers are Paratech Holdco Limited, and the name of the product is QTC Test Processing Unit. Quantum tunneling composites, or QTCs, as mentioned before, are composite materials of metals and non-conducting elastomeric binder. At normal conditions, that is, without pressure, they act as insulators, and when pressure is applied, the resistance decreases exponentially. These sensors use piezoresistive composite materials based on the quantum tunneling effect and are perfect for making touch sensitive skins. QTC Touch Processing Unit is an ARM based resistive multi touch system with pressure scanning and interpolation of acquired data. However, the only drawback is low repeatability. We provide you with a comparison of the different tactile sensors existing in the market today.